Welcome to another episode of Packet Brew. Today we will discuss one of the oldest and simplest routing protocol, which is Routing Information Protocol, also known as RIP. In this video, you will learn how it works, its versions, and characteristics. RIP is treated as an ancient protocol, but did you know that it is actually the key to mastering BGP, the protocol that runs the internet? By the end of this video, you'll see exactly how RIP's distance vector concepts evolved into BGP's path vector intelligence that routes traffic between Amazon, Google, and your ISP. Let's start with the foundation. What is RIP? RIP is a distance vector routing protocol used in computer networks. It's like a neighborhood gossip network. Each router acts like a neighbor who knows the best way to get to various destinations. And every 30 seconds, they chat over the fence, sharing what they know about how to get to places. How RIP works. RIP uses hop counts as its metric. A hop is simply passing through one router. The best path to any destination is the one with the fewest hops. What happens when you configure RIP? First, the routers will be on initial state wherein they only know about directly connected networks. And then comes the information sharing. Every 30 seconds, routers broadcast their entire routing table to neighbors. After that, the router learns the update. It adds 1 to the hop count and updates its table if it's a better path. After sharing information and learning updates, eventually there will be convergence in the network, where all routers learn the best paths to all destinations. There are two known RIP versions. First is RIP version 1, which is formally documented as RFC in 1988. It only has classful routing, no subnet mask information, broadcast updates, and no authentication. Eventually, it was enhanced to RIP version 2 in 1998 to fix its limitations. RIP version 2 has classless routing support, includes subnet masks, multicast updates, authentication support, and route tagging. RIP has several built-in mechanisms to prevent routing loops. Maximum hop count. RIP has a maximum hop count mechanism where it restricts the network size to 15 hops to prevent infinite counting when loops occur. Routes with 16 plus hops are considered unreachable. Next is split horizon. Split horizon is a mechanism where the router never advertised the route back through the interface where it learned the advertisement to prevent loops. For example, if router 1 learns about network X from router 2, router 1 won't tell router 2 how to reach network X. Route poisoning. Sending a route with max metric of 16 to tell neighbors that it is unreachable. Next is split horizon with poison reverse. This is an enhancement of split horizon. In this case, the router actively advertises unreachable routes with metric 16 back to source to explicitly tell neighbors to not use it for the destination. It's like confirming that the route is poisoned after it receives a route with max metric. RIP also has hold down timers. This timer kicks in when a route goes down. It tells the router to wait before accepting new information about it to prevent route flapping. It's 180 seconds by default. Lastly are triggered updates. It's a mechanism to send immediate updates when topology changes for faster convergence. It's supported in RIP version 2. RIP has different timers. Update timer, 30 seconds for regular updates. Invalid timer, 180 seconds. Route becomes invalid. Hold down timer, 180 seconds, prevents flapping. And the flush timer, 240 seconds, before the route is removed from the table. There are advantages and disadvantages when using RIP. For advantage, we have simplicity, automatic, standard, and small networks. For disadvantages, we have slow convergence, limited scalability, inefficient metric, bandwidth waste, and count to infinity. Here's where it gets interesting. RIP's distance vector algorithm has similarities with BGP's path vector approach. RIP shares hop counts, while BGP shares AS paths. RIP prevents loops with split horizon, while BGP prevents loops by detecting its own AS in the path for eBGP. RIP updates neighbors periodically, and BGP maintains persistent TCP sessions for reliability. BGP essentially took RIP's tell your neighbors what you know concept and scaled it to handle the complexity of internet routing between thousands of autonomous systems. Let's do a quick configuration in Packet Tracer. We'll use a simple topology with 3 routers directly connected with each other. RIP will be enabled on all routers. IP addresses are shown in the diagram. To enable RIP, enter Global Configuration Mode and use the router RIP command. On most iOS devices, the default is RIP version 1, so we need to configure it as version 2. Then configure the network that will participate in RIP using the command network address. Enter no auto summary command to disable automatic summarization to classful subnet. RIP is like the bicycle of routing protocols. Simple, reliable, and perfect for learning. It teaches fundamental routing concepts that apply to all modern protocols, making it an essential stepping stone in network engineering education, even if you'll likely implement more sophisticated protocols in production environments. That's a wrap. If you like this type of video, like and subscribe for more network engineering content. See you next time!